the logic. So this is joint work with Anthony Lin, sitting in the audience, Moses Granadi and Georg Zetsche, and it appeared at Popple this year. And Ramsey quantifiers, we will get applications mainly in verification, but there's also connections to synthesis. And for example, in the context of constrained horn clauses. Okay, what is it? And I want to take this as a motivation to get started. So what are constrained horn clauses? I think we have seen this several times. So it's essentially just an implication where on the left-hand side, we have some conjunction of a constraint, which is a formula in some first-order theory. And we have conjunctions of uninterpreted predicates. So those we call queries. So all the variables are universally quantified. And on the right-hand side, we either have a constraint or a query. And we can also have a system of those now. So we have a conjunction of those constraint horn clauses. So what one usually does is, in the context of safety, is one can use this to express safety conditions. Like in this example here, we have a program with two variables, x1, x2, they're inputted. And we say, okay, they should both be integers that are greater or equals 0. And in our loop is just, okay, we add 1 to x1, and as long as it is strictly smaller than x2. One safety question one could ask, okay, can x1 become negative? Of course it cannot, but okay, constraint horn clauses allow us to formulate this actually in the logic. So we say, okay, we have to define some constraints to do this. So we have some initial constraint, which we have that x1 and x2 are greater or equal 0. We have a transition relation. Here the y1 and y2 are the new values of the x1, x2 after one step. So in this case, we say that the new value of x1, should be larger by 1, and the x2 doesn't change. And then the bad states, we don't want to go negative in x1, so we say that this is actually x1 smaller 0. So now, okay, with constraint horn clauses, we can define an inductive invariant. So inductive invariant just says, okay, it contains the initial configurations. If we are in the inductive invariant and we make another step, then we are still in the inductive invariant, and it does not intersect with bad. Okay, and if we have a solution to this, then our program is safe. And in this case, we can just take the initial configurations, essentially. So what I want to talk about is, instead of safety, is liveness. So the problem here with liveness is that this cannot be expressed in constraint horn clauses. We have to extend this. Yeah. So in our program, we can check a liveness problem, which is termination. One could try to express it. Okay, what if we do not take this inductive invariant, but we take an over-approximation of the reachability relation now? So this you can express in constraint horn clauses. And you say that the transition relation is a subset of R. And if we are in R and make another step, then we're still in R. Okay, so the problem here is now, okay, this would be a possible solution. That just x1 is getting bigger and bigger, strictly bigger. But this does not tell you anything about termination. So yeah, this is not enough. So there are several ways to do this now, to actually force R to be good enough to show you that this program terminates. So in the context of constraint horn clauses, what one does in the literature is, for example, one adds a specific predicate that tells you, okay, that with that you can check that R here is well-founded, essentially. But this is not expressible in constraint horn clauses a priori. This is an ad hoc solution, really specific to the termination problem here. So, and what I want to propose is, instead of adding this ad hoc predicate, what about extending the logic itself? So what about extending the logic with a so-called Ramsey quantifier? And I will show you some reason why this may be worth studying, but why this maybe is the right extension to do this liveness problems then. So what is the Ramsey quantifier? So we have a formula like this. We have vectors of variables, x and y. Those are bound by the Ramsey quantifier. And we have a vector of free variables, z. So when is this now fulfilled? So this is fulfilled for evaluation C of the three variables, if and only if there exists an infinite sequence now of vectors of elements. We want them to be pairwise distinct. such that for every I smaller j, we have that phi ai aj c holds. So what does this mean? So we pick some valuation for the set. Then this formula here essentially becomes a binary relation of vectors. So this can be seen as an infinite graph. And now we want to check if this infinite graph has an infinite clique. So in this case, a directed clique, because we want that I smaller j. So let's take a look at some examples. So down here, we say, okay, we have the Ramsey quantifier on x and y. We want that x is smaller than y, and we want that still x is bounded from above by z. So this means our sequence, so if we want to fulfill this formula, we have to find an infinite sequence of elements such that it is strictly increasing, but it's still bounded from above by z. So of course, it depends now on the logic, on the structure or on the theory that you're looking at this, if this is satisfiable or not. So if you're taking the integers as your domain, okay, you have no chance to satisfy this. Every infinite sequence of integers, of course, that is strictly increasing is unbounded. But if you are taking the reals instead, you can have this convergent behavior. So actually, you can find an infinite clique here. The problem is that, as I said, we choose the valuation of the set before, and then we check our infinite clique. So what if we do it the other way around? So what if we add now the set as an existentially quantified variable within the scope of the Ramsey quantifier? So now also over set, this is satisfiable because what you can do now is for every pair of x and y, you can choose a new valuation for the set. So you can make the set larger and larger for each x and y. So actually, you can find an infinite clique also in the integers here. So we will also discuss here a bit what existential quantifiers or how they can be dealt with here. So let's come back to constraint horn clauses. As I said, we want to extend this framework now. So to check termination here, we first of all do not want to have a loop in R. As I said, in an infinite clique, every vector should be pairwise distinct. So this is more like a technical condition that, okay, we have to also take into account that something can repeat, but this can be already expressed in CHC. So what is really new here is now this, okay? So we are on the left side on our constraint horn clause, we can state something with Ramsey quantifiers. So we do not want to have an infinite clique here. And if you do not have both, then we know that the program terminates. I guess it's quite easy to see why this holds. So one solution now to our program here would be to say, okay, x1 is smaller y1, so x1 is getting bigger. x2 is equals y2, which means, okay, x2 just stays the same, is constant. And we have that x1 is smaller x2. This means, okay, so this is actually the same, quite the same example as we had here. So the x1 is bounded from above by x2. And x2 does not change. So we cannot find an infinite clique. So this is, this is actually fulfilled, and this also, so, okay, our program terminates, fine. So I have now two conditions. So I mentioned two conditions now. We have this well-foundedness condition that's in the literature, and we have this no loop and no infinite clique condition. So how do they relate? So if we are just looking at the as R to be the reachability relation, so the transitive closure of the transition relation, then it doesn't make a difference. So then it's just equivalent. But in general, we are looking at this over-approximation. So this could be non-transitive, right? So, and what I say here is that actually this condition here now, that there's no loop and no infinite clique, is a weaker condition. So it is fulfilled by more R's. So more solutions for R fulfill this condition, but it's still enough, as I said, to prove termination. So to see this, let's consider this example here, where we have a transition relation T, which is just, okay, I can go from I plus 1 to I for all natural numbers. So I go not below 0. And as an over-approximation, we could, let's say, synthesize, or let's say some input, whatever, gives you this relation here. This is an over-approximation where you just say, okay, I can go from I to j if I is greater than j for I and j natural numbers. And if I go below 0, I can only make one step. I don't have these transitive edges. So on the left side, I'm transitive, right? But on the right side, I'm not. So in this example here, this is not well-founded because I have this infinite decreasing chain here to minus infinity. But we don't have an infinite clique. because we do not have these transitive edges here. And here we also do not have an infinite clique because this is bounded from below. So this is a weaker condition. So, and I quickly want to talk about, okay, how can we do this actually for other liveness problems? So what about non-termination? So this is also not expressible in constrained Horn clauses. So here you would in fact need an under-approximation of the reachability relation instead of an over-approximation. But in this example, one can actually come up with the reachability relation itself. But actually an under-approximation would suffice. I don't want to go into detail here, but so if we have a reachability relation or an under-approximation, then okay, we can check with the Ramsey quantifier, does there exist an infinite sequence in this? So, and if it does, okay, it's non-terminating. We proved non-termination. The problem here is now, okay, how do we want to check this? Actually, we want to use SMT solvers, right? The problem is, okay, SMT solvers do not allow us to write something with Ramsey quantifiers. So our approach will be to eliminate it. We eliminate the Ramsey quantifier, we get another formula that can be fed into the SMT solver, and then we can check satisfiability. And here for this, it will be important that at the end we do not get wide quantifier alternations. We only get existential quantifiers if we start with an existential quantified formula. This brings me to our main result. So if we are starting with an existential formula in some linear arithmetic, so this doesn't come in SMT theory, like over the integers, or the reals, or both, like this is the mixture where you can actually take the floor operator, or you can check for integer as you want. And we can construct a polynomial time of a formula that is only of linear size, which is also only has existential quantifiers, such that it's equivalent to this Ramsey quantified formula. So this means that we eliminated the Ramsey quantifier with only a linear blowup and in polynomial time. But here be aware that we have existential quantifiers here. And there are more existential quantifiers than we had at the beginning. So it was already known for quite a long time. So the first paper was by Schmerz and Simpson in the 80s for the integer case, and Dangen-Niebara for the real case, that you can actually eliminate Ramsey quantifiers in these logics effectively. But the complexity was high. So there are two problems why it was high. So one problem was that at the end, this will give you multiple quantifier alternations, their techniques. And as I said, okay, SMT solvers do not like multiple quantifier alternations. So and this will blow up your procedure. And another problem is they already assume that you're given a quantifier-free formula. And here I say, okay, actually I want to take existential quantifiers here also. So what you have to do here at the beginning in these procedures is to somehow get rid of those existential quantifiers. So of course, and quantifier elimination is expensive. What we do is we show, okay, if this existential quantifier appears within the scope of a Ramsey quantifier, we can actually move these variables in the Ramsey quantifier, and then we get rid of the existential quantifiers, and then we eliminate the Ramsey quantifier. And this will only have a blowup of linear in size. Okay, so let me show you how this works. So as I said, phi should be now an existential formula. So phi has at the beginning some existential quantified variable w, and x and y is just our Ramsey quantified vectors. So as in the example, this means that for every pair in our cliques, so this is a clique, of course, possibly bigger because we are working with infinite cliques, but let's stick with 3 here. So, and for every pair, we choose a new evaluation for the w. So the u is here evaluation for the w. So we can check for A, B, we can choose U. For B, C, we can choose V. For A, C, we can choose W for W. It's also not so good. But so what we say is that this formula is actually equivalent now to the following formula. Here we do not have any existential quantifiers anymore in the scope of the Ramsey quantifier, but we have these more Ramsey quantified vectors. So this tells you that actually we can always enlarge our vectors here of vertices, and then instead of an arbitrary element, we always choose the sum of the first additional guy, the left-hand side here, and the second additional guy of this here, and then just take the sum. So of course, if you have a clique like this, then you also have a clique like this. The other direction is actually the non-trivial direction, but I don't want to go into detail here. Okay, so we got rid of existential quantifiers. Great. So we can assume that our formula is now quantifier free, but we still have the Ramsey quantifier. So now we want to eliminate this. And one could first try to actually define the clique itself. Maybe find an expression for the clique itself, but this is not possible already in integer arithmetic. So let's take a look at this example where you say, okay, I want to find an infinite clique that is strictly increasing, but exponentially. So y is 2 times x, and then there's some other condition on x, let's say. So this is an exponentially increasing sequence, and this is not definable in linear integer arithmetic, so it's not ultimately periodic. But what we do is, instead of defining the clique itself, we define a condition that holds if and only if the clique exists. So in this example, you can come up with a condition, okay, I want an infinite sequence such that psi of ai holds, so this additional condition holds, and it's just strictly increasing. So here note, okay, this is not an infinite clique here. So the other direction, of course, so if you have a clique like this, but that is exponentially increasing, then it's also strictly increasing, but the other way around, it's only existence equivalent. So you have this sequence here, and then you can always take a subsequence such that the gaps are exponentially large. Okay. And this is, in some sense, the main idea, of course, simplified, but let me quickly show you what the proof looks like. So let's assume we have only a conjunction of inequalities. Yeah, we have on the left-hand side the x, on the right-hand side the y, and some free variables z and some constants. What we want to do is we want to, okay, we are given some sequence of valuations. We want to check, okay, how does the left-hand side here and the right-hand side evolve in our sequence? Okay, this looks a bit scary, but actually what we do is we guess some values. Those are called profiles. Yeah, we guess some what we want to be the supremum of the left-hand side and some bound on the lim-inf of the right-hand side in some sequence of a's, so a case here. We pick some sequence, then we say, okay, this should fulfill this profile conditions here. We call such a sequence compatible with this profile, and we say that a profile is admissible if this left-hand side guys here are strictly smaller than this right-hand side guys, or this is already omega. So why does this make sense? So let's assume on the left-hand side we are unbounded, so we are increasing, but it's unbounded. And on the right-hand side, it's bounded, let's say, constant. Then, of course, at some point, this will be greater than this, so this inequality will not be fulfilled anymore. Not for infinitely many values, right, in our sequence. So there we cannot find an infinite clique. On the other hand, let's say that this is also unbounded from, that's also increasing and unbounded. So both are unbounded. Then for every infinite sequence, we can find a subsequence such that they always fulfill these inequalities for every pair. So we have an infinite clique. So this is essentially the idea. So one can show that this Ramsey quantified formula here is fulfilled if and only if there exists such an admissible profile, so such a nice profile, such that there is a sequence that is compatible with it for some valuation of the free variables. And the key feature one uses here is that one focuses on sequences of a special form. Sequences that are have some offset a0 and then some multiple of some other vector a. And essentially those vectors will all be guessed with existential quantifiers. Yeah, we guess this profile here with existential quantifiers, and we guess this a0 and a with existential quantifiers. Then one has to show, okay, actually it's enough to look at those sequences. Okay, I said we can do more liveness than just termination or non-termination. So let's take a look at this example here. So this is a Bucci condition, what we want to check here. And it's a form of linear liveness. So here we have a program that starts with 0, and then we just add 3. Okay, what about, okay, can we reach an even number here of x1 infinitely often? Of course, it's a pretty easy example, but so this is a Bucci condition, right? So we want to reach some set infinitely often.
What is x1?
X. What do you mean?
x1, what is x1?
Where's x1?
x sub 1.
Ah, sorry, this should be x. Yeah, there's a typo. Okay, there's only x. Yeah, I changed it. At the beginning it was x1, but we only have one variable. Okay, we want to check if x can be even infinitely often. So we define our constraint. So here the reachability relation is easy to see that it is expressible in linear arithmetic. And the set of configurations that we want to reach infinitely often is just, okay, x is divisible by 2. Now we can use our Ramsey quantifier and say, okay, we want to find an infinite clique, infinite sequence of configurations such that we can reach one from the other. And we want to reach this even here infinitely often, but we can always take a subsequence. So we can always say, okay, we want to reach it every time in the sequence because we can have multiple steps between them. So how do we check this? Okay, we now know how to eliminate actually the Ramsey quantifier. And now the nice part is that we can now use our favorite SMT solver to check this liveness problem here. So as I said, this liveness problem is a linear liveness problem because the condition we want to reach here infinitely often is in linear arithmetic. So we have some precise complexity results here as our application. So as I said, linear liveness is one of them. And for various classes of systems, this will give us a precise complexity. So for example, if you look at continuous vector addition systems with states, reversal bounded counter machines, where we can also allow one counter to have to be unrestricted. So reversal bounded means, okay, I'm changing the mode from decreasing to increasing and vice versa at most a bounded number of times. Then we have a Parik automata and one counter automata. So the reason that for all of them it is NP complete is that we can actually construct the reachability relation, so this transitive closure of the transition relation in polynomial time. And we get a formula that is in the existential fragment of linear arithmetic. So here we really need this existential stuff, and not that we have to eliminate these existential quantifiers to get the precise complexity. And another application is here checking well-quasi-order. So this arises in the context of well-structured transition systems. And here the problem is you are given some formula in linear integer arithmetic. It's quantifier free. And is it a well-quasi-ordering? Okay, you have to check, okay, transitivity, reflexive. Okay, but that's easy. But then you have to check well-founded. So, and why it is co-NP is that, okay, it is well-founded if there exists, if there does not exist an infinite sequence such that between every pair, they are not in relation. So our Ramsey quantifier can help us to get co-NP complexity here. And it's actually a precise complexity. And the last I want to talk about is monetic decomposability, which is also a problem, a well-known problem here in verification, where you're given some formula in linear arithmetic. It has multiple free variables, let's say x, y, z. And now you want to check if these variables can be decoupled. You can find a Boolean combination now of unary formulas, so formulas that only depend on one variable. So those variables are independent from each other. So this has several applications, for example, in constraint databases, where these simplifications of formulas can really help you speed up things. And this problem of monetic decomposability can be shown to be co-NP complete for all of these linear arithmetic logics here I talked about. So the proof idea, or the connection to a Ramsey quantifier, it's maybe not so apparent here at the beginning, but is that this problem can be reduced to a check of finite index of equivalence relation. So a formula is monetic decomposable if and only if certain equivalence relations have finite index. And we can check finite index of an equivalence relation by just taking the complement of the equivalence relation and then check for an infinite clique. So here we get co-NP. To conclude, so I've shown you, okay, we can eliminate here Ramsey quantifiers in linear arithmetic, which are common SMT theories, and then after that, we can use our SMT solver to check satisfiability. We only get existential quantifiers instead of alternations of quantifiers, and we can even start with existential quantified formulas. We have applications and verification that give us precise complexity results, and most notably, I would say we get a general framework to do liveness in if we are guaranteed to get the reachability relation or an approximation thereof as an input. We do not show you how to get this reachability relation. We only show you, okay, if you give us this reachability relation or an approximation, we can check for you safety liveness properties. And what I mentioned at the beginning, which is actually an open problem, is can we extend something like constraint horn clauses that we can use Ramsey quantifiers within the constraint horn clauses? So I showed you evidence that this may be what we're studying because you can do it in SMT theories, but can we actually extend constraint horn clauses such that we do not have to make this ad hoc assumption of checking well-foundedness, but maybe it's a nicer generalization thereof. And that's it. Thank you.
Ade, please, Moshe.
Can you go back to 14?
Yeah. Okay, sorry.
Yeah. Suppose you, quasi-ordering, suppose you just define it in first order logic. Okay, just a property. You just put no Ramsey quantifier, just you put all the properties of full quasi-ordering. Is it possible? Is it first order definable?
No.
No, it's not first order definable. Okay.
Since Moshe asked this guy, just ask for the corollary, and then I put my. And if you have for O phi, it's still okay because you negate it will be existential, no? So
but what do you mean
just allow one universal quantifier for in the second corollary. Because your negation is existentials, and then you apply your machine. This was just a curiosity.
Yeah, I guess so. Yeah, seems to me like so. Yeah.
I had another question actually. So
yeah,
you have this approximation with about well-foundedness with R loop and R clique.
Yeah,
it's approximation, but so sometimes you can massage your relation so that you prove it with R loop and R clique that relation is well-founded. Sometimes it's not.
Yeah, but I said that it's a weaker condition, right? It's
Yes.
actually a better condition than well-foundedness.
Yes.
Yeah.
So is there some technology to massage this relation so that you can then check it with loop and clique? I come with something, I want to know that it's well-founded. It doesn't satisfy loop and clique, but you can tell me, oh yes, but I can give you another relation that...
No, I don't know if I can give you another relation actually.
This would be nice because this would be like...
I've never thought about it actually.
No, it's not always the case, but it's...
Okay, just let's have one last question, please.
I was wondering about various extensions of this idea or slightly orthogonal. So, for example, if you extended arithmetic by these limited divisibility predicates as you have in automatic structures, so x is power 2 and divides y, or if you got rid of addition completely and just had multiplication, Scholar arithmetic, I'm wondering sort of evidence from the theory of automatic structures that you can get rid of quantifiers in these cases. And then the final idea is, okay, what if you forget integers and you just go to Tarski's arithmetic? So
yeah, so I mean, okay, one thing I didn't mention is like also in automatic structures. So the Ramsey quantifier is regularity preserving, right? So also in automatic or tree automatic structures, you get a tree or automatic relation at the end. But yeah, so for example, Scholar arithmetic is tree automatic. Okay, you can, but what we do not know is for all of these stuff is can we actually eliminate the Ramsey quantifier in the logic itself? So for example, for nonlinear arithmetic, we know actually that it is possible. It's eliminable, even effective, but we do not know the complexity, precise complexity. But yeah, so I guess this is the natural next step to identify, okay, what other logics allow us to eliminate the Ramsey quantifier.
Okay, let's thank the speaker once again.